Hello everyone, I welcome you to this video content. This video explores the pin diagram, block diagram, memory management and interrupt signals of microprocessor 8085. This video lecture presented by Dr. R. Pushpavalli, Assistant Professor of Computer Science, Sri Sharda College for Women, Autonomous, Salem. The 8085 microprocessor is an 8-bit processor developed by the Intel company in the late 1970s. The 8085 processor played an important role in the development of modern computers and embedded systems. Its architecture and instruction set have influenced the design of many subsequent processors. A microprocessor pin is a small electrical connection on the microprocessor chip that allows to communicate with other components in the computer system. Microprocessor 8085 consists of total of 40 pins. Each pin has a specific function, contributing to the overall operation of the processor. Pins which are divided into 6 functional groups such as address bus or pins, data bus, control and status signals, power supply and frequency signals, externally initiated signals, and serial I/O port. Here, pins carrying the signals and buses are group of pins or wires that carry the related signals, which enabling the communication and data transfer within a computer system. Address bus are typically the unidirectional, which means it carries the signals in one direction only from the microprocessor to memory or I/O devices. Here the pins from 12 to 28 we called as a address bus. Usually the 16 signal lines are used as address bus. However, these lines are split into two segments. Pin from A15 to A8 and pin from AD7 to AD0. Here A15 to A8 are unidirectional and are used to carry a higher order address of 16-bit address. The pins from AD0 to AD7 act as a dual purpose, one for addressing the memory and transferring the data. Here, multiplexed address or data bus can used carry the lower order address and data bytes. The pins from 12 to 19 named as a AD0 to AD7 we called as a multiplexed address or data bus, which means these pins are multiplexed. They are able to serve as a two purpose. Lower order address bit. It can carry the lower order address bit to specify a memory location for transferring the data. Here the data bus acted as a data transferring purpose. It carried the data bytes during the data transfer between the microprocessor and memory or I/O devices. Here the VCC and ground are two signals used to maintain the proper voltage level of the microprocessor by providing the necessary power and ground connection for the microprocessor to function correctly. Here two pins are considered as a power supply pins, the pin number 40 and 20. The pin number 40, voltage common collector. It refers the positive power supply of voltage. That means it carries the 5 volt of power. The main purpose of this pin provide the necessary power to the microprocessor. The pin number 20, voltage source sense or ground. It refers the name VSS. It carries the 0 of volt. And the main purpose of this VSS provides a common ground reference for the microprocessor and other component in the system. The control pins in the 8085 microprocessor facilitate communication between various components. Here ALE, AD-WR- and IO bar memory dash are the pins comes under the control and status pins. ALE means address latch enable, which indicates the lower order address is available on the line number AD0 to AD7. Then AD dash enables or control the read operation from the memory or I/O devices. The signal W or dash, which controls or permit the write operation to the memory or I/O devices. Finally, I/O bar memory dash, which determine whether the address is for I/O or memory. The 8085 microprocessor has several externally initiated signals that allows to the interact with the external devices and respond to the external events. Some of these signals include the interrupt signals, INT or interrupt request. This signal is used by external devices to request an interrupt, and RST 5.5, RST 6.5, RST 7.5. These are vectored interrupts that can be triggered by the external devices. The TRAP, that means non-maskable interrupt, that has the highest priority among all other interrupts. The reset in. This signal is used to reset the microprocessor. The hold and HLDA signals. The hold signal is used by external devices to request control of the bus. Here, HLDA acknowledges the hold request. Ready signal. The ready signal is used by external devices to indicate that they are ready to transfer the data. The serial input data and serial output data signals in the 8085 microprocessor are used for serial communications. SID, serial input data, is used to receive the serial data from the external devices. Here, SID allows the microprocessor to receive the data one bit at a time. The SOD, serial data output, is used to transmit the serial data to the external devices. The SOD allows the microprocessor to transmit data one bit at a time. The SID and SOD signals are useful in the application that requires serial communication, such as the serial communication protocols. SID and SOD can be used to implement the serial communication protocols like RS-232. The interfacing with the several devices. SID and SOD can be used to interface the 8085 microprocessor with several devices like serial keyboards, display devices, or other microcontrollers. The S0 and S1 pins can be used to determine the type of the operation being performed, such as S1 and S0 are both are 0 means now the operation is instruction fetch. The value of S1 and S0 are 0, 1 means now the operation is memory reading. Here the memory writing operation, the value of S1 and S0 is 1 and 0. Both are 1 means now the operation is IO read or IO write. Let us see the block diagram of 8085. The screen flashes the block diagram of 8085 microprocessor, which has several key components. They are arithmetic and logical unit, which perform the arithmetic and logical operations, data bus, which helps to transfer the data between microprocessor and memory or IO devices, the address bus, which carries the memory address from the microprocessor to memory or IO devices. The control bus in the 8085 microprocessor consists of several control signals that manage the data transfer and operation execution. The registers in the 8085 microprocessor are essential for performing various operations such as arithmetic, logical, and data transfer instructions. Here the accumulator is a 8-bit register that stores the result of the arithmetic and logical operations. The flag register also a 8-bit register that stores the status of the flag like sign bit, 0 and carry. The general purpose registers are B, C, D, E, H and L. Sometimes the registers can be used as a register pairs. The BC is used for handling the 16-bit operations and DE register pair used for 16-bit operations. HL is a separate pair. The instruction register which hold the current instruction being the executed. The program counter which keeps the track of the memory address of the next instruction to be fetched. The stack pointer manages the stack, a region of memory for storing data temporarily. The timing and control unit which generate the control signal for the microprocessor's operation. The instruction decoder interrupts instruction fetched from the memory, converting them into the control signals for execution. This component is essential for determining the operation to perform based on the opcode input. The control unit, which coordinates the operation of the microprocessor by directing the data flow between the ALU registers and memory. It generates the control signals that are critical for the timing and sequence of operation. Here, the memory interface is responsible for connecting the microprocessor to external memory devices, which handles the data input or output between the CPU and memory, ensuring data integrity and proper timing. The ROM and RAM both are the internal memory which helps to store the data internally or temporarily. The RAM means random access memory, the ROM means read-only memory. And then the ROM is again classified some different types. The ROM means read-only memory, PROM means programmable read-only memory, and EPROM is erasable programmable read-only memory. The input-output interface connects the microprocessor with peripheral devices, enabling the input and output operations which manage the signals to the devices such as a keyboard, display and other storage devices, which also facilitates to the user interactions. Next, let us see the memory management of the 8085. The 8085 architecture has a memory unit. The memory unit can classify into two types, primary and secondary memory. The primary memory includes the RAM and ROM, read-only memory and random access memory, while the secondary memory refers to the storage device like hard disk, SSD and pen drive like that. The memory mapping in the 8085 defines the arrangement of the memory addresses. This mapping allows the microprocessor to interact seamlessly with various peripherals, devices and memory segments, which facilitating the structured data handling. Let us go with the interrupt signals in 8085 microprocessor. The interrupt signals were classified into two groups. They are hardware interrupts and software interrupts. The hardware interrupts are RST 7.5, RST 6.5 and RST 5.5. The TRAP is the software interrupts. Here these enable the processor to react the various signals from the I/O devices and internal events. When the interrupt signal is received, the 8085 pauses the current operation or current execution, save its current status and then jump to the predetermined memory location to handle the interrupt. This ensures timely responsible to the urgent task without losing important data. Once the interrupt is recognized and being processed, the microprocessor sends an acknowledgement signal back to the device that initiated the interrupt. This confirms that the interrupt request has been received and is being addressed appropriately. The hardware interrupt versus software interrupt. Hardware interrupts are generated by the external devices, while software interrupts are initiated by the executing specific instructions within a program. Both types of interrupts are playing the vital role for handling the task dynamically and improving the system responsiveness. The priority of the interrupts. The microprocessor has defined the different priority for the interrupts based on their urgency. For example, TRAP is the highest priority interrupt, which ensures the critical task and execute the first. Preventing any delay is handling the essential functions. The application of the interrupts are many. For example, it manages I/O operations and do with real-time data processing and support the multitasking. It enables the microprocessor to handle the multiple processes efficiently, improving the overall system performance. Thank you for watching this video.